Good day. Let's have ourselves another interesting session for chemistry. Now, in our previous session, we looked at various concepts. We talked about the concept of the empirical formula. We looked at how the empirical formula could be used to translate towards the molecular formula. Thereafter, we now moved from the molecular formula and talked about how we could use the molecular formula to find out the different formulas for different kinds of compounds. It is very, very important to put this in perspective. Today, we are now going to be talking about something along the lines of those different material structures we have. Do not forget that matter forms the basis for almost every single concept we check and research as far as chemistry is concerned. Today's session, we will now look at matter in detail, as well as the different kinds of theories, relationships, conundrums, concepts that now hold together to form the concept around matter that we study in chemistry today. This is going to be our focus in this session. Now, to begin, we must first and foremost create a general understanding as to what matter stands for. So, matter. On a very basic empirical level, we say that matter is anything that has mass and occupies space. Fine. That makes all the essence and concept we need for matter. Let's now go beyond that. Matter and its material forms that exist is such that it consists of atoms, molecules, and ions. Do not forget that in some of our earlier sessions, we have dedicated enough time to talk about the concept of atoms, molecules, and ions. We talk about atoms being the smallest individual part of an element that can exist freely on its own. We then modified that definition into the fact that atom in itself can actually be divisible. And then within the atom, you can have three major constituents, which is the proton, the neutron, and the electron. We talk about the fact that the proton and neutron exist within the nucleus of the atom, and then the electron revolves around that atom, around the nucleus of that atom. Thus, we saw from the Dalton's definition of an atom towards the modified or modern definitions of what atom is. We talked about the molecules being groups of atoms or groups of constituents that flock together and share some peculiar characteristics among themselves. We talked about ions being charged, whether it's a positively charged ion, which is also referred to as a cation, or a negatively charged ion, which is also referred to as an anion. We talked about the fact that these charges consist or come as part of the essential feature of elements having to go into reactions. Do not forget that the goal of every single element is to achieve stability, nobility, or to achieve an octet structure in its outermost shell. So elements go into reactions in order to balance up whatever they are left with, so that they can achieve an octet structure. Some will prefer to give out their electrons, as in the case of metals. We call those ones electron donors, and some will prefer to accept more electrons to complete their structure. We call them electron acceptors, and we find out that non-metals are predominantly acceptors of electrons. We have looked at all of that in our studies of the constituents of what matter is. Now, let's go a step further. We can also talk about matter in terms of the physical states matter bear. We talk about the physical state of solidity, we talk about liquid states, and then we talk about the gaseous states. So matter can either exist as a solid, as a liquid, or as a gaseous state. This is held true in every single kind of matter we find. In fact, if we were to split along the periodic table, we will find that these three states still hold predominance over the periodic table. We find that the group 1, 2, 3 elements are usually solid in nature. Then the 4, 5 that are in the middle sometimes bear to become liquids. But the 7, 8 groups are predominantly gaseous in nature. In fact, the group 8 elements, which are called noble gases or inert gases, from their names, you would already find out that they are gaseous in nature. So this gives us the physical state or consistency of what matter is, as a solid, as a liquid, or as a gas. Now let's now put all of this into perspective and talk about the core concept of what we are going to be discussing today. The first core concept we are going to be looking at is the kinetic theory of gases. The kinetic theory of gases. So we can put this as our start point for today's session. Now, what exactly are we referring to when we talk about the kinetic theory of gases? The very first thing you have to know is that the basis for the kinetic theory of gases comes from the forces of attraction between particles and energy that those particles possess. The kinetic theory of gases talks about the forces of attraction between different particles and the energy those particles possess. In fact, the kinetic theory of gases can be summarily put into a concept around 6 major assumptions. With these 6 major assumptions, we can put forward what is termed as the kinetic theory of gases, as well as provide ourselves with a differential understanding of what kinetic theory of gases talk about. Let us talk about the first major assumption under the kinetic theory of gases. The very first thing is that a gas consists of tiny molecules. But that's not all. Even though it consists of tiny molecules, these molecules are moving randomly. They are moving randomly, but that's still not all. In this random motion that they are moving, it is still continuous. So, the first assumption under the kinetic theory of gases is that the gas consists of tiny molecules. And these tiny molecules are moving randomly in a continuous motion. So let's give ourselves an assumption. Let's give ourselves a kind of imagination process. Recall that if you were to pour water into a kettle, and then you were to heat up that kettle, either with your hot plate or with your gas or with your stove or with your firewood or whatever heat source you like, the moment that water in the kettle gets boiled up, you'd find out that it starts bubbling. And then you find out that the molecules within that water source, of course, they are bubbling together, but you cannot pinpoint what manner of motion they are having. They are moving in such randomness that you cannot even say this particular water molecule is at this point, and then, okay, it's staying at this point and it's not moving beyond this point. It's moving so randomly. So that water molecule at this point could move on to the other section without you even knowing. Why? Because at boiling point, the water molecules that is inherently liquid has already started becoming gaseous. So they have started showing resemblance towards this kinetic theory of gas. So that is a very good imagination scenario for you. Within that boiling point where the water molecules are becoming gaseous in nature, you find out that that randomness of motion begins to become very, very predominant. And then within that random motion, it is not stopping at any point. It is a motion that is continuous. The water molecules are moving randomly and continuously. So long as that heat level is maintained and they are going beyond that boiling point, that random continuous motion will continue. That is the first assumption under the kinetic theory of gases. Let us talk about another one. A second assumption we can have under the kinetic theory of gases is the fact that the molecules of gas collide with one another. And I feel like this is something that we should be able to follow. It doesn't just collide with one another alone. They also collide with the walls of the container. So the molecules of gas collide with one another and with the walls of the container. This is true in all cases. Again, if we look at the scenario with the boiling kettle, the water molecules that are now inherently gaseous, that are moving in random continuous motion within the kettle, are being indiscriminate. They are hitting one another. They are hitting one another. The moment they keep hitting one another, that is what causes that scenario we term as bubbling out or evaporation, as the case might be. Because they are hitting at themselves at so much pace and intensity, of course, when two water molecules that are now in bubble forms hit, there is no way one of those bubbles, or at least both of those bubbles, will get blown out. And then the moment it's blown out, there is gaseous release, and then you see evaporation comes in. So that comes because of the collision between those molecules. But they are not just colliding with one another alone, they are also colliding with the container that houses them, within the walls of the container. Another way to look at it and be sure that they are actually colliding with the container is if you now pick the content of the kettle that is now very, very hot, and then you pour it into a cup. And then that cup, you cover that cup with a lid. After a while, if you were to open that lid, you'd find out that on the surface of the lid, there is already water molecules formed on the surface of the lid. You'd wonder that you didn't pour any water on the lid, you just left the lid on top, and probably you poured the water into the container at half level or half filled, so you felt that there is no way there should be any water on the lid. But then because of the concept that those waters which are now in gaseous form, they are moving in random motion and continuously, and they are colliding with the walls of the container, regardless of the fact that there is space within them. In fact, because of the fact that there is space within them, it allows the possibility for them to continue to collide, right? So that is why within the walls of the container, even on the top part of the cup where there is no water constituent, you will still find water molecules around. This is what this second assumption talks about. Let's look at another assumption for this. Under the kinetic theory of gas, we talk about the fact that the volume of the gas itself is negligible. The volume of the gas itself is negligible. And when we say negligible, we are saying that it's very, very small. How do we know this? That is because they are continually carrying out processes of motion. Because of the fact that they are carrying out processes of motion, it means that they are not in a still structure. They are not still, they are not stable, they are continually reacting, exciting with themselves. Because of the fact that they are not still, it becomes very, very hard to measure whatever mass, or should I say whatever quantity or volume they would have. They are continually in motion. For instance, if you have your water source within the kettle, or you pour your water within the kettle, you already know how much or the volume of water you poured in the kettle. It's easy for you to measure. Why? Because you have picked that measurement from its liquid state. Very good. There is density. There is all of that. You can easily measure the volume, no problem. But then because they have started getting excited, you'll find out that you cannot, in that period of excitement, you cannot correctly say you want to measure the volume of the water molecules escaping into the atmosphere. Why? Because at that point, the volume of those water vapor escaping into the atmosphere, their volume at that point is very, very negligible. They are escaping as bubbles. Now imagine if you were to take a bubble in your hand and you were trying to measure the volume of that bubble. You would have as much problem as you would ever imagine. Why? Because in that process, they are excited, so you cannot have a volume measurement, which is something you should have in a stable state. This is why we say that the volume of the gas itself is negligible. You will find out later on that whenever we now want to talk about the volume of the given mass of gas, we always talk about that volume with respect to the container. So we use the volume of the container to have a rough estimate of what the volume of the gas would be. Why? Because we know that if we were to measure the volume of the gas itself, then it would be negligible. However, we could fill the container with as much gas to a certain level where it is completely saturated and it can no longer take in any more gas. That is why it suffices for us to be able to measure the volume of the container. Let us move on to see what other assumptions we have. We can simply say that the collision, of course, we have already said earlier that the molecules of the gases will collide with one another. The collision between these gas molecules is in fact perfectly elastic. The collision is perfectly elastic. Now, with some concepts in physics that we have learnt in some of our physics live sessions, you'll find out what we mean by perfectly elastic collisions and perfectly inelastic collisions. In essence, when we talk about perfectly elastic collisions, we are talking about a recurrence, or should I say, a reminder, or should I probably say in clearer terms, the resolution of whatever force that were occurring before the collision with respect to the force that occurred after collision. There is still perfect elasticity between those two forces. So while the gas molecules are continually excited and carrying out random motion, the moment they collide, whatever force they themselves were exerting before collision remains even after collision. There is no loss. There is no scenario where there is now a conjunction or coalition between two or more molecules together after collision. No. Once they collide, they are still having as much energy in order to split off. So it is kind of a collision repellence case. A collision and an immediate repel between both colliding molecules. So that's why we say that the collision between gas molecules is in fact perfectly elastic. And because of the fact that the collision is perfectly elastic, we can now draw one more assumption from this process of collisions within the gas molecules. And what's that assumption? We can now say that the gas molecules are completely independent of one another. The gas molecules are completely independent of one another. And it follows because they are colliding and then immediately they are splitting off. There is no coalition. There is no combination between them. They are colliding and they are splitting off immediately. They are repelling immediately, right? And they will continually collide because it is a continuous random motion. So because of this, we can easily say that the gas molecules are independent of one another. There is no force of attraction between them at all. There is no force of attraction between them. We have a measure of the energy they use within the collision process, as well as we understand the fact that when they collide, they repel. So because of this, we can simply say that within that excitation period, there is no force of attraction between them at all. We can now add, in addition to all of this, and say for conclusive purposes, that if we were now to measure it in terms of the kinetic energy and the temperature necessary to carry out this excitation process, we can now say that the average kinetic energy is in fact directly proportional to the absolute temperature. We can now say that the average kinetic energy is in fact directly proportional to the absolute temperature. What does that mean? It means that the more the temperature increases, the more the rate of collision will happen. And if that rate of collision is happening, obviously it's tantamount to saying that the kinetic energy, which is the energy required to carry out that continuous dynamic motion, that energy is in fact increasing. So the more the temperature, the more the energy. The more the energy, the more the temperature. So there is an increase scenario between them. It's a direct proportion, a proportion which would obviously have talked about in your mathematics life class. Proportionality, when it's direct, means that when the first party increases, the second party is also increasing. If the first party decreases, the second party would also decrease. So once the kinetic energy is increased, then the temperature is also increased. Or if the temperature is increased, then the kinetic energy is increased. That is why we can easily talk about water in a kettle when it reaches boiling point, because the temperature has been increased towards that boiling point. And as the temperature continues to increase, the rate of collision and the rate of random movement and continuous random movement will continue to also increase with it. This is what we understand under the kinetic theory of gases, and it has been put together in these assumptions so that we can have a holistic overview as far as what kinetic theory of gases stands for. Now, let us now move a step further. We have talked about the kinetic theory of gases. We have understood the state of randomness, the state of collision. We have understood the state of movement that exists within these molecules of gas. Now, let us talk about some important concepts that we have within this study of gases, and then move on towards the various kinds of rules and dependent properties that exist in order to govern all our reactions or all our situational reactions within gases and without gases as well. We will consider some 3 or 4 major important concepts of the gases. We will first and foremost talk about the gas volume. Remember, I'll recall that we said that under the assumption of the kinetic theory of gases, the volume of the gas in itself is in fact negligible, and that we could now extrapolate this in order to talk about the volume of the gas with respect to the volume of the container. So let's put all of this into detail. So when we now talk about the gas volume, or the volume of gas, or the given mass of gas, we are always going to be defining it as the space the gas contains, which in essence is us talking about the container that contains the gas. So when we talk about the gas volume, it is talking about the space or the enclosement that contains the gas. And of course, as we have mentioned earlier, this is also the same thing as us talking about the volume of the container that encloses the gas. It is measured in either meter cube. So SI of measurement is either meter cube or the centimeter cube or the decimeter cube, as the case might be. So you'll find out that in fact in practical chemistry, you are always, or usually we use the decimeter cube measurement. You may have 22.4 dm cube and so on and so forth. You must get yourself familiar with all these terminologies. The next, we will talk about the concept of the temperature. Very important. Remember in our assumptions of the kinetic theory of gases, we talked about the fact that there is a direct proportion between the energy and the temperature. So if the temperature increases, then the energy increases. So what is exactly this temperature we are talking about? Let's use the blank definition. We talk about the temperature as the measure of the degree of hotness or coldness of the body. So this is the blank definition, and this is very, very valid. The measure of the degree of hotness or coldness of the body, whatever the body is. So you have your kettle, you have poured water into it. You want to follow the process of heating for this kettle. You want to know exactly where that random motion starts. So you are following the degree from 0 degrees to 2 degrees to 3 degrees to 10 degrees to 15 degrees to 20 degrees. So you get 100 degrees Celsius and you'll be like, oh yeah, at this point, the randomness has kicked in. The continuity of random motion has kicked in, and all these concepts have kicked in. That is because you have been able to measure the degree of hotness or coldness of that particular body. Now, how do we measure it? The absolutely valid or generalized measure of temperature is in fact the Kelvin. Of course, we have other measurements, which is the Celsius, which is also the Fahrenheit. However, in terms of theoretical